Hey everyone, welcome back to the JNTUH concepts. And in this video, we are going to discuss the uncertainty principle and wave particle duality. These two topics are going to be discussed in this video. So, in our previous video, we have covered what is meant by superposition and what is meant by entanglement. So, superposition, entanglement, uncertainty principle, and wave particle duality. These four are the fundamental principles in quantum technologies. So if you are new to this channel, don't forget to hit the subscribe and do like this video. So without any delay, let's get into the topic. Uncertainty principle, a fundamental concept in quantum mechanics that states that certain parts of physical properties like position and momentum cannot be known both with an unlimited precision at the same time. So it is the general definition of what is meant by uncertainty principle. The formal statement is it is impossible to simultaneously know both the exact position and momentum of a particle. So we have also studied this topic in our class 12 or class 11 physics. The uncertainty principle for momentum and position can be expressed as delta x into delta p greater than or equals to h by 2 pi. Here delta x is nothing but the uncertainty in position and delta p is uncertainty in momentum. We know that momentum equals to mass into velocity. As here the momentum is uncertain, so we consider the velocity as uncertain, as mass is fixed. So the changeable or the uncertain element is velocity. So instead of delta p, you can also take this one, delta x into mass into delta velocity, which is greater than or equals to h by 2 pi. H is equals to Planck's constant, which is 6.626 into 10 to the power of minus 34 kilojoules or kgs per second. So till now we have studied that uncertainty principle is only about momentum and position, but from here the uncertainty principle is not only about position and momentum, it is also applicable for other pair of objectives like energy and time, etc. So the same expression for energy and time, delta E into delta T greater than or equal to h by 2 pi. Here delta E represents the uncertainty in energy, while delta T represents the uncertainty in time. H is fixed Planck's constant, that is 6.626 into 10 to the power of minus 34 kgs per second. Uncertainty principle plays a major implication for the behavior to explain the zero point energy phenomena. So what is meant by zero point energy phenomena? It states that the particles have motion even at the absolute zero temperature. It is not due to measurement errors or bad instruments, but it is the fundamental property of nature. It defines how precisely quantum states can be manipulated or measured. Uncertainty principle has huge impact in quantum cryptography. It has reshaped our understanding by replacing the classical idea of determinism with a probabilistic framework. We know that quantum technologies or quantum mechanics is based on the probabilistic framework. So uncertainty principle played a key role in quantum cryptography to develop the deterministic framework to the probabilistic framework. A conceptual framework or a conceptual example. It is nothing but a real world implication of uncertainty principle. Imagine trying to take a photo of a speeding car at a night. If you use a long exposure or wide zoom, then we can only see the motion or momentum of the moving car, but the exact position gets blurred out. If you use a short exposure, we can freeze the position, but we can't see the information about how fast the car is moving. So it's a good example. So imagine a car moving in a X amount of speed at night. So if you use a wide zoom, you can only see how fast the car is moving, but you can't exactly capture the position of car when you click the photo. But if you use the short exposure, you can exactly freeze the position of the car in the picture, but you can't see that how fast it is moving. That's the example for an uncertainty principle. Quantum mechanics only allows probabilities for these values limited by values. The sharper we try to pin down a property, the blurrier the other becomes. So just as now we have seen a real world example, it depends on how much precisely you want to see the car is moving. The more you try to capture the exact position of the car, the harder it becomes to capture its speed. The more harder you try to capture its speed, then the same way it becomes harder to capture its position. Wave particle duality, a fundamental concept in quantum mechanics which reveals that all quantum objects like electrons, photons, atoms, light, matter, etc., exhibit both wave like and particle like properties depending on how you observe them. This dual nature was discovered in early 20th century. During that time, light was understood as a wave which has the ability to interfere and diffract. But in 1905, Sir Einstein showed that light is a stream of particles called photons and explained this concept as the photoelectric effect. So the famous photoelectric effect came out from this wave particle duality. The photoelectric effect states that the light comes in energy packets called quanta but not in continuous waves. Later on in 1924, Sir de Broglie introduced the concept of matter wave and assigning wavelength to any particle based on its momentum using the relation lambda equals to h by p. So as time passed from 1905 to 1924, Sir de Broglie also added their observations to showcase the wave and particle like properties of light. So he assigned wavelength to a particle. Here lambda is nothing but the wavelength and h is equals to Planck's constant, whereas we know p is nothing but momentum, that is mass into velocity. The wave particle duality challenges our classical intuition and suggests that quantum entities exist in a superposition of possibilities until they are observed. When they are observed, they fall into either state or they become deterministic in nature. Quantum particles do not behave strictly as particles or waves, but as a blend of both. If you measure position, they appear like particle. If you measure or observe their path, indirectly they exhibit wave-like interference. This dual nature defies classical expectations and forces us to adapt a probabilistic interpretation of nature. This concept not only underpins the foundations of classical physics, but also drives the functioning of quantum technologies like electron microscopes, quantum computers, etc. A conceptual example for this can be the double slit experiment. If we send photons or electrons through two slits, they form an interference pattern that is a wave-like behavior when they are not observed. Also, they form a particle-like pattern or behavior, like hitting one slit to the other. We should understand that the same particle acts like a wave and or a particle depending on the measurement setup. So that's how the wave particle duality is understood. So till now we have covered two topics, that is uncertainty principle and wave particle duality. So summary of this video can be, the first one is uncertainty principle. It states that we can't measure simultaneously two properties with the same level of precision. The precise way you move forward for a single property, the harder it gets to capture another property, that is uncertainty principle. So coming to the wave particle duality, it states that particles like electrons, photons, etc. exhibit both wave-like and particle-like properties. So that is the simple definitions of both concepts. So I hope you have understood these two concepts in this video. So with this one, we have covered the fundamental principles of quantum technologies. So in our next video, we'll be moving forward to the next topic. So if you haven't subscribed to JNTUH concepts, do subscribe, do hit the like button. So that's it for this video. Keep learning.